Hey, I'm Brandon Conkle, and on this channel I talk a lot about seeking determinism in software engineering with more reliable tools and patterns. I cover the Rust programming language quite a lot because of its unique approach to memory ownership and lifetimes, which I think goes a long way to help with reliability and performance. Today I want to talk about event-driven APIs using Rust with AWS Kinesis. Event-driven APIs are often seen as complex and heavy, requiring beefy servers to handle streaming message brokers like Kafka at scale, and generally adding a lot of operational complexity to your deployment. I recently wrapped up a great client project for Nearform, where I built a more lightweight event-driven architecture based on AWS ecosystem services like DynamoDB, Kinesis, and Lambda functions, and it performed beautifully at national scale. It handled moderately heavy traffic across many retail facilities in multiple AWS regions. It scaled smoothly. It handled unreliable third-party APIs and things like that with a lot of fault tolerance. And I really just loved how it came together. Nearform gave me some time this month to create a demo project that shows off a very similar architecture. On that project, I used Go, but here for my demo repo, I used Rust. And I think it worked out even better than the Go version did. I built it out with Lambda functions that serve as both the API and streaming event handlers that handle events that come through the Kinesis stream. I'm really excited to show it off because it's a much more lightweight approach to event-driven microservices that won't break the bank and won't need a whole team of DevOps specialists to maintain. I'll be following up this video with a blog post soon on the Nearform blog, going into more detail about the high level of the approach and its benefits. But for this video, I'm going to dive in pretty deep to the Rust code and show how I brought all the Rust pieces together to work really well in the Lambda context. So first off, event-driven architecture itself. Every application deals with events, even if those events are implicit and never actually called out anywhere. So for example, creating a meeting invite would typically involve events like meeting created, meeting updated, invite sent. Even if these aren't formally defined as events in the code base, they're there, they're happening. Everything that happens can be called an event. But event-driven architectures promote these events to first-class citizens, even going so far as to derive the current state of an entity based on the events that have happened over time, rather than just using a current snapshot of the state. This approach is really flexible, and it can help you stay responsive and keep up with complex business logic by spreading it out across smaller decoupled components focused on particular concerns, making those components more flexible and making it easier for your team to manage all the mischief in an intricate system. It's a great fit for systems that benefit from more granular scaling, more granular fault tolerance within individual components, and it provides a lot of flexibility in situations where you don't have a good understanding of access patterns or data needs up front, because you can radically change your schema and have an old version running alongside a new version for your horizontally scaled pods or containers to access based on what version they're at in the middle of your rolling deploy. All those kind of really big challenges that you have with distributed systems seem to come together really well in this approach. Paired with strategies like CQRS, which is command query responsibility separation, meaning you've got a separate write store and a read store or multiple read stores based on your needs. You can iterate really quickly. You can deploy rapidly. You don't need to bring the whole system down. It just comes together really well in my experience. I think AWS is a great platform to deploy this on. I'll cover this all in more detail when my Nearform blog post is published, but I think AWS has a good set of on-demand services that scale really smoothly and consistently from tiny hobby projects all the way up to globally distributed systems. And it's very reliable and consistent. You're not going to have to spend a lot of time tuning the scaling and trying to get it to work just right, because Amazon's setup, their on-demand services work really well and handle just massive amounts of load, even in big spikes, without a whole lot of configuration and hand holding from your DevOps team. I think Kinesis specifically, I prefer over alternatives like Kafka or EventBridge or SQS, specifically because it's not too complex. It implements an opinionated workflow that's great for event sourcing using event streams that broadcast one-to-many or many-to-many. It fits in easily with other AWS services. It offers that smooth auto scaling I was talking about, really similar to DynamoDB. In fact, I'm fairly certain behind the scenes Kinesis is built on top of DynamoDB, especially given some of the error messages I've seen at times. The strategy we used on my recent project involved a global DynamoDB table used as an immutable event log, streaming events to Kinesis and being handled by multiple downstream handlers implemented as Lambda functions. So let me pull up my diagram here to show what I mean. So this is kind of a simplified diagram of the AWS architecture. Like I said, really similar to the client project that I just got off of. The client project was using Kubernetes out front, but I instead used API Gateway because especially V2 of API Gateway is really efficient. It adds very little overhead and it allows you to invoke a Lambda function to handle your HTTP requests. So again, it fits in great with that on-demand, smoothly scaling service that you don't have to provision a lot of resources from up front that go idle for a long time. Love that aspect of AWS's services. I've had my gripes with AWS over the years, but their on-demand scaling works well. So with this API gateway setup, I've got an Axum process. Axum is a great library for HTTP handling in Rust, and it commits events. So if there's a difference between queries and mutations. In GraphQL lingo, you've got queries and mutations. In CQRS lingo, it's commands and queries. So a command is when something's changing, when something is being mutated, and each command is handled by a CQRS library that I'm using in Rust. And this gives you a central place to apply business logic. Anytime you have a command, it's essentially a request for change. And your business logic can be built into those command handlers to first identify, is this even a valid request? Is this command valid? Should it be allowed? And then you can apply any other kind of logic that you need to determine what that resulting event should look like, what the change to your entity should look like. So when the command is handled, an event is committed, one or more events, you could have multiple events that result from a command. They get committed to your event log. And so I used a DynamoDB global table for this. And global tables are awesome because you can define multiple regions for them to exist in. And Amazon handles really smooth and consistent and responsive replication across those regions. Especially if you're not using global secondary indexes or things like that, it's very fast. You don't have to worry too much about eventual consistency, and it synchronizes across those multiple regions very well. And you can have separate streams for each region, which I'm taking advantage of here so that I can format my events and publish them on Kinesis. Now, I've seen people take events directly from DynamoDB and dump them into Kinesis, but that's kind of awkward for your downstream handlers, especially on other teams that might not be using DynamoDB or things like that, because DynamoDB has its own special JSON structure, which adds like a layer of typing over top of it and really adds a whole lot of noise that's hard to sift through if you don't already have DynamoDB tools to do this. So I take a Lambda function that is triggered by my DynamoDB stream, and I format it as a consistent domain event. So I'll take the Dynamo blob and I'll deserialize it into my Rust structure for a domain event, and then publish that on my Kinesis stream so that the downstream handlers get a much cleaner experience and don't have to deal with the DynamoDB JSON mess. So each region gets its own stream. You can see I've got US East 1 and US West 2 highlighted in my diagram here. I've got the US West 2 collapsed because it looks identical to the US East 1. And for many events, you want those to be handled, you want them to be reacted to in multiple regions. So for example, I've got my projections here. A projection is something that takes the events and builds up something like a query store, a SQL table to query against, a Elasticsearch index. It could be doing other things like saving an audit log to S3, like I've got highlighted here. But these are generally things that you want to happen in all of the regions. So if an event is committed, you want all of your regions to be updated with the new details from that event. But then you also have some cases where you want a side effect. You want something to happen once in response to the event, but you don't want to duplicate that in every region. So I've got a filter criteria set up here. And my strategy for this is to handle the side effect for an event in the region it originates from. So if my request came through US East 1, if it got load balanced there, then I know that region is active. And so that region's Lambda function should be able to handle the side effect for it. But then the other regions can ignore it. They don't have to handle the side effect because they know the US East 1 region is going to handle it because that's where the event came from. It's really smooth automatic failover. If you've got good load balancing set up and US East 1 goes down for some reason, then you won't have any more events coming into US East 1, so you don't have to worry about the side effect handler in US East 1 triggering. Your events will come in through US West 2 or any other regions that you have, and the side effects will be handled there. And so you don't have to flip a switch for failover or anything like that. It's automatically distributed. If US East 1 is down, then no more events will come through there, and you don't have to worry about the event handlers triggering in that region. They'll trigger in the region that the events get routed around to, since US East 1 is down. Let's see. Yep, I think that was all that I wanted to highlight here. But basically, you can do a lot of different things with your projections and you keep them isolated. So for example, if Elasticsearch goes down for some reason, maybe you hit the storage limits or something and you've got to resize things before you can proceed. That's okay because everything else in your system is working. The fault tolerance works really smoothly across that decoupled line from each Lambda function. So Elasticsearch is down, that's okay. Those events can fail, and then you can replay those events later once Elasticsearch is back up. That's where that resiliency against external API services going down and things like that comes from. I've had a third-party source of truth that I was synchronizing with my own source of truth internally. And when their servers go down for a few hours, it's okay because everything else is still working, and I can replay those events and synchronize with the third-party service later. That kind of fault tolerance is kind of a holy grail in systems like this because it really helps you work around a lot of instability and unpredictability. To dive into the Rust code, let's talk about committing events. So the Rust code is what runs inside API Gateway and handles classic HTTP requests. I'll go ahead and pull up my code base here and show off what it looks like. There we go. So I'll start with my main.rs. You can see I have a repository set up, event-driven architecture under my bconcle name. Go take a look at it. It's got a good README with that diagram that I just showed a moment ago. But here is the main entry point for the API process. So this is main.rs. This is what runs inside the Lambda function that API Gateway triggers on HTTP requests. And I have a little utility here. This is running on Lambda function. All that does is check for the AWS Lambda runtime API environment variable. That's the word I'm looking for, to see if this is running inside a Lambda function, because I also want to be able to run it locally. I have a local stack process set up. You can see my Docker Compose here, so that I can run it locally. I can iterate really quickly without having to deploy things out to AWS. We don't have to have an environment for every team member, which I've seen on other projects, which really inflates the cost a lot. So I like being able to run it locally, and I also like being able to run CI tests with it. When I create a new PR and when I add new commits to the PR, I want to run through my integration tests, but I don't want to have to do that pointing at a deployed AWS environment. So local stack really helps you gain more flexibility and reproduce what AWS is doing for you without actually having to deploy anything. So my main process here checks for if it's running on Lambda and sets up logging a little differently depending. And then it also looks for a local stack endpoint environment variable. And if there's a local stack endpoint variable, it configures my AWS config to point at that instead of AWS's actual services. You can see me setting up some things for my dependencies. I'm using Axum's state container, which is their really lightweight dependency management. So basically, you can see I have two dependencies, tasks repo and tasks CQRS. This example repo is based around the idea of a to-do app. It's very oversimplified, but it kind of gives you an idea of how something like this would work in production in a more complex scenario. But the CQRS library here, that dependency is for handling commands, and the repo here is for handling queries. This repo is just a really simple separate DynamoDB table that's like a key value store. It's got the ID and then a snapshot of the most recent state after the last event there. If you want more flexible, more sophisticated querying that traverses relationships or handles fuzzy matches or things like that, then you would want to have a separate SQL database or an Elasticsearch index or something like that that gets updated through these Kinesis events that I'll talk about. But this tasks repo thing is just a dead simple ID key value store for the most basic of queries that DynamoDB can handle exceptionally fast. And the CQRS dependency here, that's a library that's based on a library that I'm using called CQRS ES. That's shared by a software consultancy out of Seattle called Serverless Technology. So thank you, Serverless Technology, for sharing your CQRS ES library. It's been great. I've loved building on top of it. So with those dependencies established, I've got my app state here. And so then you can see me setting up an Axum router. I add a logging layer there. And then I set up my tasks and my tasks/ID. These are my different REST endpoints. So there's the post endpoint for create. There's the patch update for patch endpoint for update. There's a delete endpoint. I'm wiring these into Axum handlers that I'll show you in a moment. And then again, I'm checking to see, is this running on Lambda? If so, I'm using this Axum AWS Lambda crate that's designed to attach Axum to a Lambda function in the context of something like API Gateway that's giving it routing information. And it handles being a general HTTP service that does its own routing really well. I've seen other approaches that use API Gateway for all the routing, and it's just kind of hard to work with. And you've got to, again, deal with those deployed resources all the time. And this gives you more flexibility to handle everything in your Lambda function with software control. If it's not running in Lambda, then it just uses an HTTP or a TCP listener, just like you would normally with Axum. So, oh yeah, and I've got just some boilerplate for handling panics. So when an HTTP request is received, I've got an http.rs file here with my Axum handlers. And so you can see I'm using the extractors to get the path component for the ID, the state to get my dependencies. And then, for example, my get operation just uses that task repo to load the record at that particular ID. My create handler is what generates this command. So I've got the create command, I've got my input, and I've got a new ID that I created. Yeah, right here. I'm using this ULID library for lexicographically sortable IDs that are a little bit better than UUIDs, in my opinion, because they're sortable. I think that's a great feature for them. So I've got an ID set up, and I include that in my command, and I include the input that came in from the HTTP request. I'll show what that looks like in a bit. But you can see I'm using this tasks CQRS to execute my command with metadata. And so the metadata is, I don't have it here, but the metadata is where I should be inserting the region that this is originating from. So note to self, I need to add the region in here. But I also have a unique command ID that can be used to determine whether a query is up to date or not yet after an event or something like that for consistency. So you can see I'm executing my event, and then I'm grabbing the resulting record from the repo to return as a response from the HTTP request. And then the update handler looks really similar. It's generating another command that it does execute with metadata on, where I need to add the region in, like I was saying. But that's generally how the mutations work. They'll generate a command, and then you'll know that you can always look for the business logic in the same place. You're going to look at it in the aggregates. Now, an aggregate is an event sourcing term that refers to the entity itself, but the entity as built up from the sequence of events that have happened before. So when you've got an aggregate, you'll know it represents the current state of an entity after all of the events have been applied to it that were stored in the event log. So the aggregate that I have is based on that CQRS-ES library, and I've got a task struct. So this task is my aggregate, it has a created at and an updated at, it has a name, an optional summary, a Boolean value about whether it's done or whether the task has been removed. And you can see I have this aggregate type. That is a constant used by the CQRS-ES library to indicate which entity this is. So the event log can be a diverse collection of events for a number of different entities. It doesn't have to be one table for one entity. You can have tasks, you can have users, you can have profiles, you can have all kinds of things mixed together in that one table, and they'll all work the same way. They'll just have different aggregate types. So I'm implementing this aggregate trait from the CQRS-ES library, and you can see this handle right here. This is the command handler. So this is where I'm matching on the command and then getting the details out of it, the ID, the input, etc. And this is where I would validate the command. Is it correct? Are all the business logic requirements satisfied in order for it to be a successful command? And if it is, then I return one or more events. So in this case, the create command returns the created event. And that's a pretty common convention in the event sourcing world. The command will be using the imperative tense, where the event will be using the past tense, because the event represents something that happened, and the create represents something that you want to happen. So you can see the create event leads to the created, or I'm sorry, the create command leads to the created event. The update command leads to the updated event. These are all things that get committed to that DynamoDB table. And once an event is committed, it shouldn't ever be changed unless you're trying to solve some tricky problem or something. But generally, the events are immutable. They shouldn't be changed. If your schema for an event changes, then your event version will change. And I'll show you what that looks like. And you can write an upcaster to upgrade old events to the newest version in a gradual way. So it's kind of like a schema migration in a SQL table or something like that, but gradually spread out. You only update the events on demand that you need to use. You don't have some big migration that updates all the events in the table or something like you would in a SQL database. And then you also see an apply method here. This apply method is what is used by the CQRS library to update the current state as each event for the entity is replayed or loaded from the event log. So this is how you say, here's what change each event makes to the current state of the entity. And this gets executed each time we're loading events from the event log. Got a couple of helper tasks here, or helper things for the task. But generally, this is the core. This is where all your business logic lives. This is going to be the heart of your domain-driven, event-driven system. So the commands, commands are pretty simple. They don't have to be versioned, because your command, it doesn't stick around. Your command only exists for as long as it takes to validate the command and generate the resulting events, and then the command's dropped. So you don't need to store this command anywhere, so it's not versioned or anything like that. But you can see the create command requires this, the ID like I passed to it, and then inputs what, what is that? The turbofish create. Anyway, this is what that looks like. Here's the input type, just a name and an optional summary. And then I've also got the update input here as well. So structuring it that way allows you to embed it easily within the event, but add extra detail. Like, for example, inputs create doesn't need an ID, but the command itself needs the ID because it needs to know what bucket to use to start committing events to for this particular entity. And so that's why I separate the inputs from the command slightly, because it makes things more flexible in other ways too. So then once a command is handled and it is successful, here's what the events look like that get committed. So for the created event, I've got the ID, the created at, and then the snapshot of the task itself, which was the name in the optional summary. For updated, I've got the ID and updated at instead of created at. You see on the aggregate over here, it has both created at and updated at, but you'll see in the apply method here, if it's created, that's when it's setting, it sets both created at and updated at that time. But then when it's updated, it just updates the updated at. So the created at stays what it is forever, essentially. I've got a couple of helper things here. I've got this that will return the aggregate ID from the event just to handle cases where you don't totally know what the event is yet, but you want to get the ID from it. You don't want to deserialize the whole thing yet, etc., etc. This little helper here, this trait for domain event, helps me keep things consistent. So I've got a consistent event type string here that I'm returning. And then there's the event version there. These are things that come from the CQRS library that I'm using. So to put it all together, I've got this CQRS.rs that initializes the CQRS framework. It gives it the table names. So I'm using environment variables to set the table names because they're different between environments. I'll have dev or staging tables, and I'll have prod tables, and then I'll have local tables that run in local stack, etc. So it's good to make those table names configurable. But I'm passing all that to the CQRS framework and initializing everything so that I can start executing events. So a quick word of caution, as I'm sure you've already spotted by now, this is way overkill for a to-do app. This is just a contrived example to show how it all works, but I wouldn't recommend a structure like this if all you have is a simple to-do app. All right, so this is my HTTP process. This is how I stitch things together there. But let's look at the infrastructure, and I will show you in the infra folder here. I've got one bucket for my AWS deployed environment. This is what I deploy out to my staging and production environments. I've got one bucket here for my local environment. This is what I use against local stack and for CI testing, etc. But they both AWS and local, use this modules folder. And I've seen people use Terraform modules, I think, in a more awkward way sometimes, where they've got reusable pieces for things that really don't have to be reusable. So the way that I set it up is I have a reusable piece here for user, because that is something that I will reuse multiple times for each user I want to add to my environment. But then for the app itself, I just have a single app module. So this is a Terraform module that sets up the whole app with all of these different pieces in just the right way that's needed for the application. But I've got it structured in a way that can be reused across the local and AWS folders. So you'll see both of them use this app module. And it puts it all together regardless of whether it's on local stack or deployed out to AWS. It uses the same configuration, which I've found is really important because you can get differences between your local structure and your deployed AWS structure that trip you up. You know, it might work locally just fine, but then when you deploy it to AWS, something weird happens. If you keep the config as close to the same as humanly possible, that cuts down on that and limits the damage there. So here is my API gateway Terraform file, and here's how I'm setting up API gateway v2 to invoke that Lambda function that has all of the command and query stuff that I was just showing. So I've got a count here. This count is because locally under the local stack operation, I'm not using API gateway. That's only being used out in the deployed environment to invoke the Lambda function. And then with local stack, I'm running the Axum process with that TCP listener I was showing you. But out in the deployed AWS environment, I'm deploying the API gateway. I've got this routes set up here to invoke my Lambda function. Whoops, there we go. So my Lambda function ARN is passed here. I've got some response parameters set up for 500 and 404 errors, but generally it just proxies through. It uses this AWS proxy integration type with the 2.0 payload format version. And that's what handles the actual HTTP request once it gets through the API gateway load balancing. And then I also have some access settings set up. I'm using a module, Terraform AWS modules. I love the Terraform AWS modules collection. They have some great modules that are set up in a way that makes them really concise and have great embedded blocks like routes and access log settings and everything. I like how they're structured. So I use those modules a lot in my code. But essentially, this is what sets it up in API Gateway so that I can commit those events to my DynamoDB event log. So next, let's talk about how we actually publish the events from DynamoDB out to Kinesis and where we go from there. So let's see, let me pull it back up. There, that's what I'm looking for, my Lambda function definition. You can see I've got a Lambda function for my HTTP API process, and I've got everything set up for it there. Give it access to DynamoDB so that it can commit the events. And then I have another one called Publisher Kinesis. So this is my Lambda function that is triggered. You can see the event source mapping shows it's triggered by DynamoDB. So it's triggered by my event log table, and I have a destination ARN on failure set up for it. So this is one of the fault tolerance features that I take advantage of here. I have this dead letter queue that's an SQS queue that I've got set up. So when these events fail to stream from DynamoDB because maybe US East 1 is down or something like that, or at least DynamoDB and US East 1 is down or something along those lines, what it'll do is it will kick the events out to a dead letter queue, and then I can replay or redrive those events. It's a button called redrive in the AWS UI to replay those events back to catch everything up once all the services are back up and running. So that's one of the great redundancy features we've got. Let's see. Yeah, I think that's the main piece here. But this event source mapping is what sets up the DynamoDB trigger. And so when anything is changed in DynamoDB, I have a binary. So a bin in your Rust crates, if you have a bin folder, that is like separate entry points. They're similar to main.rs, but they're alternate entry points for your application. So I have two separate entry points here, one for Publisher Kinesis and another one I'll talk about in a moment for this S3 audit projector. But the Publisher Kinesis bin is just an entry point. So it sets up some tracing. It sets up all the config needed to initialize my handler. And then it runs the Lambda runtime from the AWS crate for it and invokes my handler for each new event. So I'm setting up dependencies first. I'm instantiating my handler. And then within the Lambda runtime run function here, I'm passing my callback function here. Essentially, this is it's called a Lambda function, but it's different from AWS's definition of a Lambda function. But basically, it's an inline function that invokes my handler here. And I'm doing it this way because it's a closure, so it has access to the outer scope where it can reach the handler that I've initialized. But from there, it goes to publishers/kinesis.rs. So this is the actual bulk of the publisher itself. It defines a type that it needs for the DynamoDB record, and it sets up a try from method so that I can try deserializing my domain event from the event log record. But here's the main entry point, this handle method here. So you can see it gets the Lambda event that comes from the AWS SDK code, and then it tries to iterate over each record, because remember, you can get a batch of records, and it looks specifically for records with an event name of insert, because if this is an update or a delete, I don't want to emit anything on Kinesis. I only want to emit things on Kinesis for new events that are committed. So once it finds that, it calls this handle record method, which is responsible for deserializing everything and formatting the domain event. So you can see I'm using that try into that I was highlighting. And then it calls put record to publish that event on Kinesis to this Kinesis stream name, which, just like my DynamoDB tables, is configurable. We're going to have a different stream name for each environment. I use the aggregate type as the partition key and send the data as a binary blob like this. And that's all it takes. It gets published to Kinesis, and then my multiple consumers can then subscribe to it. So those downstream handlers are what I'll talk about next. I will pull up the S3 audit handler. So if you remember my diagram, I'll go back to the diagram here. This would be the audit log projection here. This would be an event handler that listens, it subscribes to that event stream, and then takes action in response to it. And like I said, you can have multiple projections running alongside each other. You can have, it's a one-to-many stream, so many can listen and respond to it. And AWS has great features around resilience for that too. I'll show you in a moment. But this is what the actual S3 audit projector looks like. It's really similar to the other thing. It instantiates the handler. It passes it, in this case, an S3 client, because that's what it needs to save a JSON record of the event to my audit log bucket. And then once again, calls handler.handle there. So in this case, it goes down to my projectors/S3 audit. And so you can see here, this really, it looks similar again. We've got a handle function here. It handles the Lambda event this time, which is a Kinesis event rather than a DynamoDB event. And it takes it, serializes it as a JSON file. It pushes it to S3. And you can see I've got a little bit of debug logging here so that I could see it actually running and verify that everything looks the way that it should. But then it calls put object to put that into the requested bucket. And I've got a nice little key structure here to keep everything organized based on the ID and sequence number. The sequence number is which event this is within the sequence of everything that's happened to that particular entity. So once again, this is really straightforward. It's simple to implement, and to stitch it together, once again, I have a Lambda function in my app module. I hate how GitHub keeps resetting the scrolling on this, but here we go. So if I go to my lambda.tf here, I've got my S3 audit projector here. And once again, it has an event source mapping, but this time pointing to the Kinesis stream. And I set it up with a batch size of 1, because that's easier to deal with when you have things where order really is important. I've got some retry events, attempts, and I've got a destination ARN on failure. So once again, I've got a separate dead letter queue for my S3 audit events. So again, if something goes wrong with S3, but everything else is working just fine, I can go back later and I can use that dead letter queue to just redrive the events back to the handler to handle recovering from failures. In my blog post that I have upcoming, I'm going to go in more detail about some of the fault tolerance concerns there, some of the quirks around redriving events from an SQS queue. There are reasons why, in some cases, especially if you're dealing with out-of-order events, you might want to use an SNS topic instead of a Kinesis stream because of the way that the SQS retries and redriving works there. But for the vast majority of use cases, a Kinesis stream with a dead letter queue in SQS is a great solution. Now, one thing that I've got here is report batch item failure. That's really important because you want it to, if you have a batch size of greater than one, you want it to be able to replay just the event that failed rather than replaying the entire batch. And so if I had been using a batch size greater than one, that would come into play there. You'll see in my S3 audit thing that I'm using a Kinesis event response. And with that, you can do a Kinesis batch item failure to identify the Kinesis sequence number for the particular item that failed. And so in that case, it will replay or retry only the event that failed and not the rest of them. In my case, though, the sequence of events is really important because you might have, a create as sequence 1, an update as sequence 2, and a delete as sequence 3. And if you process those out of order, that would be a problem. Let's see. I think that covers just about everything here. Yeah, that's all the major pieces of it. You can see a couple of other little surrounding things. So like in my domains/tasks, this is where the aggregate was and the commands and events. I also have a thing called view here, which this is that really simple ID key value store that I was talking about. This helps it update that in a consistent way. I've got, this is my config. I need to get back out of that. Yeah, I've got like a top level errors object that uses this error to define the different errors that can happen. And then I've got this domain event type to reflect my formatted domain event after it's been restructured from the DynamoDB structure. And then I've got a few utilities here, like my Lambda tracing thing for setting up logging the way that I like. And I've also got this update type, which was borrowed essentially from async GraphQL to represent something that could be 3 different states: unchanged, set to empty, or set to a particular value. And that really helps for partial updates, for patch updates. But in general, there you have it. That's how I have things set up. And in my blog post, I'll show off a little bit more about it working in action. I'll show some screenshots from AWS, the deployed environment that I've got it in. But this repository is here. You can take a look at it and pick it apart up until my blog post is published and play around with the ideas. Try to get it working yourself. I've got a little bootstrap script so that you can deploy it to your own AWS environment with your own credentials and everything. So let me know what you think. Let me know how this works out for you. I think that it's a really flexible approach that has done a great job for keeping things lightweight enough that a small team of just a few people can maintain a service that's used, nationwide for a very well-known retail household name, and without requiring a huge team of people to maintain it and keep the servers going and everything. I think AWS gives you some great tools for managing things a lot more simply, and I love the results here. Thanks for watching, and I'll follow up with another video soon for a completely different topic. I've been experimenting with using Rust to build Node API modules so that you can take advantage of the flexibility and ease of use, ease of onboarding for Node APIs. But then when you really need performance, when you really need strict resource control, or you want to do things that Node is not particularly good at, like CPU-bound concurrency and things like that, then building a module in Rust that's a native module that can be invoked from Node is a really great way to approach that. So be on the lookout for that video coming soon, and Thanks for watching.